Okay, let's get going because I need to get through this section in the next hour. I'm also pretty sick. So if you see me like adding layers or removing layers, this is because I'm feverish and I'm like alternating between being shivering and sweating. So I'm going to do my absolute best to get through this. But if I start having like fever dreams and saying things that are like incomprehensible and wrong, maybe just raise your hand and say maybe we should call it. But I think we'll be all right. This is Lemsip. I am drinking it. Hopefully it's fast acting. Okay. So I've been talking a lot about stuff, mainly number systems, and trying to convince you that the polynomials with integer coefficients can be a stand-in for a type of number called the algebraic numbers. And yesterday, we went through all of the algorithms for doing things like sums of polynomials and products of polynomials and being able to do quotient and remainders on polynomials. And sort of I like glazed over the GCD algorithm, but it's in effect, it's just the same thing that you would do for any other Euclidean domain. We just have to use all of the polynomial infrastructure that you have been building. Now, this is all supposed to be culminating in today's lecture, where I'm going to show you how we're going to use all of those tools to factor polynomials. And I gave you a little task yesterday saying, suppose that we're able to solve the problem of integer factorization. Can we use that to do polynomial factorization? Did anyone manage to work that out? Okay, so I'll show you now. Okay, but before we talk about the strategies for factorization, we should talk about like what factoring even means. So if we have a composite integer, what it means to factor a composite integer is to break it into a product of primes, where like the primes are somehow the building blocks of all the other numbers. So what should our primes be for polynomials? You know, they're on the board, but let's humor me. Yeah, something that's irreducible. We want to take a polynomial and we want to decompose it into a product of polynomials and stop when the polynomial can't be factored anymore. It is no longer reducible, for which we call this irreducible. So the technical definition of an irreducible polynomial is that a polynomial A is irreducible if for all ways to decompose it into polynomials B and C, one of them is going to be a constant, right? So this is important though. We don't care to distinguish polynomials that are off by a scalar. Why do you suppose this is the case? We're interested in solving polynomials, right? Finding their roots. Yeah. Yes, if you have x minus 1, its root is 0. If you multiply that by 2, you get 2x minus 2. Oh, sorry. X minus 1, its root is 1. If I multiply that by 2, you get 2x minus 2. Its root is still 1. You can multiply by anything you want, and it leaves all of the roots invariant. So we get to basically multiply our polynomials by whatever we wish, because it doesn't really affect the thing that we're searching for. And it certainly it's something that we can correct for afterwards, right? So we have to think of polynomials being equivalent to all of their scalar multiples. Irreducibility depends on the coefficient field, right? So let's look at this. So suppose we have the polynomial x to the power of 4 minus 4. Depending on where we're allowed to do the factoring, we're going to get different compositions. So if we're restricted to decomposing this into two polynomials with integer coefficients, then that's as far as we can go. X squared minus 2 times x squared plus 2. Those cannot decompose. If we say, oh, you're actually allowed to use all real numbers here, which in fact allows us to access all of the algebraic numbers, then actually this can split a little bit further. Like the x squared minus 2 has roots plus minus square root of 2. And if we're allowed to use the complex numbers, then we get to split totally. And have you ever heard this term splitting field? So the complex numbers are called the splitting field because they have this property, right? A splitting field is a field that allows you to take any polynomial and factor it into linears, like linear polynomials totally. And the complex numbers is an example of such a splitting field. Okay, we're going to focus on factoring polynomials with integer coefficients. Now, why is this sufficient? Well, I said we don't care about multiplying through by polynomials. So if we do happen to have a polynomial which is has rational coefficients, just multiply through, get rid of all of the denominators by multiplying by some scalar, right? And only get rid of all of them. So we don't really lose anything by focusing on factorizing over integer polynomials with integer coefficients. Now, here's the first way that we figured out how to factorize polynomials that was developed in the 1970s. So the other thing I want to emphasize is that the beginning of this computer algebra journey started in the 70s. This is pretty recent technology, right? Within the last 50 years. Those of you who are mathematicians are probably studying stuff that's like centuries old, right? So this is really new. Suppose we have a polynomial 9x to the power of 4 minus 1. And I evaluate that polynomial at x is equal to 10. And we get the number 89,999. Right, we're looking at this line. Okay, but I said suppose we have integer factorization. So 89,999 factors into 7 times 13 times 23 times 43. Now we can use that factorization to kind of guess. We can use the factorization of the integer to guess the factorization of the polynomial, right? Because if we evaluated this polynomial at 10 and it broke into these integer factors, then perhaps 7 came from x minus 3, right? That's what we get when we evaluate 10 minus 3. Perhaps 13 came from x plus 3. Perhaps 23 came from 2x plus 3. And perhaps 43 came from 4x plus 3, right? This is what you get. If you evaluate that polynomial on the right at 10, you're going to get that number. Now, this is a guess, right? So how can we confirm that this actually is or is not the factorization? You just take any of these factors and you try to test divide 9x4 minus 1. Remember, we have a remainder algorithm for polynomials. So if we get a clean division, if we get no remainder on division by x minus 3, we found one of the factors, and then we can remove it and just repeat this, right? We have a smaller problem and repeat this. But so it turns out that none of these factors actually divide that. So what do we do now? Well, okay, so we have no linear factors. Maybe there are quadratic factors. So here we can go look for quadratic factors. So I know that this integer factorizes into 7 times 13 times 23 by 43. So now I just have to group them by 2s and like try to make these same types of guesses. So 7 by 13 is 91. And we can arrive at 91 by 100 minus 10 plus 1, which is x squared minus x plus 1. Oh, but damn it, this doesn't divide f, so it's not a factor. Okay, let's try one of the other pairings. 7 and 23, that's 161, which is 200 minus 40 plus 1, which is 2x plus squared minus 4x plus 1. But damn it, it doesn't divide the original polynomial and therefore is not a factor. Okay, let's try one of the other pairs. 7 and 43, that's 301, which is the same as 300 plus 1, which is 3x squared plus 1, which does divide f. So we found a quadratic irreducible factor of the polynomial. We remove it, and then we just repeat this, right, to factor what's left, which is smaller. We may get luckier by choosing different evaluation points that have fewer integer factors, right? So if I used 12 here instead, then we're going to get, we have this polynomial evaluates to 186,623, which factors into 431 and 433. And since there are less factors here, we get more, it's easier to sort of guess at these factors. Now, why isn't this sufficient for doing factorization then if we have an algorithm for doing it? Pardon me? Who took number theory? Is primality testing easy? Is integer factorization easy? Isn't the fact that integer factorization is hard like the precondition for cryptography to work? It's not computationally efficient. It's not purposeful to reduce our problem to another algorithmic problem that's slow, right? We want something that's fast. But something that was slow was better than nothing in the 1970s. But I want to show you something that's fast, that's clever. Okay, but before I can show you the fast, clever algorithm, I have to introduce just a few more pieces of terminology because we sort of need to sanitize the polynomials coming in before we try to factor them, just to try to make the problem a little bit more manageable. Okay, so we discussed already that I don't care about scaling factors. So what I want to do is remove the GCD of all the coefficients. I want to remove as much of the scaling factors as if I have 2x minus 2, I want to remove 2 to get x minus 1. Right, so this is called the content of the polynomial. The GCD of all of the coefficients of the polynomial is called the content. And if we then divide out by that content, what left is called the primitive polynomial. Right, so this is the first piece of terminology I need. A primitive polynomial is a polynomial that has unit content, right? The GCDs of its coefficient is 1. The second thing I need to introduce is the notion of a polynomial being monic. And a monic polynomial is any polynomial that has a unit leading term. Now, it's really easy to make any polynomial monic because you just look at its leading term and you divide by it. And so it's not going to be too hard, at least computationally, to get a primitive polynomial and to make that polynomial monic. And so the content of a polynomial is the GCD of its coefficients, namely this. And the primitive part of the polynomial is just the polynomial divided through by this content. And this is a scaling division. This isn't a division among polynomials. So for example, if you have 6x cubed plus 3x plus 3 is equal to, why is this an equation? Oh, because content is here. The content of 6x cubed plus 3x plus 3 is 3. That's the GCD of all the coefficients. So the primitive part of this polynomial is itself divided through by its content. So dividing this by 3, you get 2x cubed plus x plus 1. So that's an example of primitive and content. Okay, the second thing we want to do is given a polynomial to factor like this, we're satisfied finding the irreducible components and not necessarily like the degrees of those irreducible components. Like the number 12 is 2 squared times 3. And suppose you gave me an instruction to find its integer factorization. And I said, oh, I lost all of the exponents. I know that prime factors are 2 and 3, but I lost all the other information. Would you be satisfied with that? Would it be hard to recover the degrees? Because you just have to do divisions, right? I'm saying 2 is one of the prime factors of 12. So I say, okay, how many times does 2 divide 12? Twice. Okay, so that was its degree, right? Test divisions are going to be not expensive. So the hard part about factorization is finding the irreducible components. We can always recover their degrees by doing just repeated divisions, right? The same way that we did it with 12 by dividing by 2 once and twice, right? So the factorization problem we're going to solve is going to assume that we never have factors that have powers higher than 1. And I'll show you how to actually ensure that before we even engage in factorization. So I just want to point out that some of these commands have already been implemented in Julia in your project. So if I have a polynomial 6x cubed plus 3x plus 3, you can ask for its content. And you can actually ask for the primitive part, but again, it has this strange interface because I'm not allowed to do divisions until I'm in a field of prime characteristic, because I need to have a field, right? We're going to restrict ourselves to working with polynomials whose coefficients are over ZP. But like one of the tasks that you have is to sort of clean up this interface by passing around polynomials that are able to reduce their coefficients depending on what prime field we're working in. Square-free polynomials. Okay, so I said we're going to reduce the factorization problem to only finding the irreducible components. So how do I get rid, like how should I explain? Okay, so I'll just explain the definitions and then it will be obvious. So I need a polynomial that factors into linear irreducible components is said to be square free because there are no squares in it. This means that there are no repeated roots, right? Because if we have like a root that's cubed, that also has a square in it, right? So I'm not saying I'm just looking for squares. I'm looking for any factor that isn't a linear factor. And the terminology for this is square free. You can't find any squares in the reduction. So a polynomial is square free if it has no repeated factors. So there doesn't exist a polynomial. If A is square free, there is no polynomial B that is non-constant where B squared divides A. That's just a logical statement of the English I said. But here's a lemma. If A is square free, then the GCD of A and its derivative with respect to X is a unit, is 1. It's not that hard to prove. Here's the second lemma. If A is a polynomial with coefficients taken from ZP, and suppose it has factorization like this. We don't necessarily know the factorization. I'm just saying, well, it has to factor into a finite many terms, where all of the linear ones perhaps are grouped here, all of the squares are grouped here, all of the cubes are grouped here. Yes, sir?
Why is A squared free when, like, for example, that sub 2 is squared?
Did I say A was square free here? This, I'm saying in lemma 1, A is square free if and only if the GCD of A.
But in the second lemma, it says B is squared free factorization.
Oh, yeah, that shouldn't be there. It should just be a factorization of it. Yeah. The derivative of A with respect to X. It's a mistake. I'll correct it. Yeah, so let A, so ignore my English. The symbols are mostly correct. The English is the thing that can get wrong. Okay, so let A just be a polynomial and we can sort of like factor it like this where all of the linear things are in F1, quadratic things are in F2, cubes are in F3. If we take the derivative of this, right, let's focus on F2. What's going to happen? Well, we're going to do product rule. So the F2s are going to be in all of the sums where we're not like looking at it in the product rule. And when it's F2 is up in the product rule, we're going to get 2F2. Right? So that means if you like expand this with the product rule, F2 is in every single summed in that derivative, which means you can extract it. Right? So what this means generally is that the GCD of A and the derivative of A is going to give you this. Yeah. No, they are irreducible, right? Because I need the linear ones to be in F1 and like the quadratic ones to be in F2. They are irreducible. Let's just leave it at that. I don't think anything else is strictly necessary. Okay, so if I take the GCD of A and A prime, I'm going to get these terms. And then if I take F and I divide it, I don't know why I switched to F here, but if I take, why did this change to F? Okay, so just imagine this. If I take, imagine this is F. So if I take F and I divide by the GCD of F and F prime, this is going to remove, it's going to make everything degree 1. Right? It's removing all of the repeated roots from the original polynomial. And the only thing that we needed to do is GCD and derivatives. We haven't yet done any factoring because like it doesn't matter. Like this is actually expanded when we're working with it. Right? It's not actually factored like this. We're just working with a polynomial, right? So if you give me F and I divide F by the GCD of F and F prime, what is left is a product of irreducibles with no squares, right? So we're assured that this is going to be square free. Does that make sense? Okay, so we're going to sanitize the input in a variety of ways, right? By making it primitive, by making it monic, and then making it square free. So that the factorization is for sure going to be what, right? A product of irreducible polynomials that are also monic, right? That's one of the benefits of making, if the original polynomial we want a factor is monic. That is, it has a unit leading term. That means all of its factors also must have unit leading term, right? So this is going to simplify things a lot. So here's an example. Here's f, right? X squared plus x plus 1 cubed, x cubed minus 3x minus 1 squared. It's obviously not square free. Here's the GCD of f and f prime. And here's what we get if we divide f by g, right? G, like this is okay. Like we can't divide every polynomial by every other polynomial, but we can divide every polynomial by any of its factors. And g is certainly some of its factors. So this is going to be a clean division. And when we do this, what we're left with is the product of irreducibles that are unit that have 1 as their multiplicity. Okay, so that's an important step as well.
Question.
Yeah.
Why, in the dilemma 2, we need the factorization of a to be in a very specific form, right? We need f1 to be raised to the power of 1 and fi to be raised to the power of I. And then in the example, we don't have that because we don't have something raised to the power of.
Yeah, I suppose f doesn't actually have to be irreducible. They can be anything that you want. I'm saying, if you take a, can you organize it like this? So that it's like some product with a 1, and then some product with a square, and then some product with the cube, right? That's how I'm saying to break it up. Although we don't actually need to break it up like that. All you need to do is believe me that given any polynomial, it has a writing like that, right? Where I can group all of the terms, all of the factors that have a multiplicity 1, and I can group all of the factors that have multiplicity 2. Because what I eventually want is to have a description of A that's exactly this, right? A is equal to some product of stuff with exponent 1. No repeated roots anymore. Does that make sense, or what else can I clarify? Okay, does anyone else have misunderstanding? So like maybe we can flesh it out. Really, the only thing you have to believe me about is that doing this produces is the same polynomial with irreducible factors that have no squares, right?
What about the example?
Okay, but this is the factor, and it has exponent 1. I'm not saying that has exponent 2. I'm saying it's a factor that's repeated once, right? And this is a factor that's repeated once, right? It's like I know the factorization of 12 is at least 2 times 3, right? I would have to add, like the original example here, where's the original example? Oh, here, right? Had this exponent and this exponent, but now they're all gone, right? So now all of this, if I were to write this, all of that is F1, right? Those products. Okay. Does that make more sense? This holds for any F with integer coefficients over X. And derivatives are fast. GCDs are fast. Divisions are fast. So far, we haven't done anything that's like really going to hurt us. You have this in your Julia notebook as well. So if you give it so here's something that's cubed. If I ask you to make it square free, it's going to return this back. Notice it's a little bit scaled. There's like this 35 in front of it that occurs because of the GCDs that we're using. But I said we don't care to distinguish polynomials by their scaling factors. So this is equivalent to the first thing. Okay, so we're in particular, what we're focusing on this project is factorization in ZPX. Because I gave you the piece of technology to take factorizations in ZP and recover the factorization over the proper integers, right? By just doing enough of them. So this really is going to be like the meat of everything, to do the factorization where we recover integer coefficients and all of the degrees. That's going to be easy, but finding originally all the irreducible factors, that is going to be difficult. Okay, so some propositions. If A is a polynomial with integer coefficients, and it's primitive, and it's square free, then I can write it like that, where each fk is an irreducible polynomial over zx. I missed the x. So if p does not divide the leading coefficient of a, then the number of factors over a is strictly greater, is at least as big as L. This is just a proposition to test if a polynomial is reducible or not, right? This is still an open question in our presentation. Like, given a polynomial, how can we tell a priori if it even has a factorization or if we're done? So we can do sort of these degree analyses. Again, this is not part of your project. I just want to mention that it is possible to do this. So if we look at this polynomial, 9x4 minus 1, I gave the factorization on the right. That's 3x squared minus 1 times 3x squared plus 1. We say a has two factors. So in the proposition before, that would be setting L to 2. But we can also factor it like mod 7, mod 5, mod 3. Like, we can look at factorizations in fields which are going to be way easier to compute in than all of the integers. So here I find 2 factors. Here I find 3 factors. Here something weird happens, right? Like, the prime actually divided the leading coefficient of a, which means when I go mod 3, that this actually disappeared. And you're not allowed to use primes where your leading coefficient vanishes. That will destroy everything. Okay, this is called an unlucky prime. So you have to make sure not to use them, right? Because 9x4 minus 1 has solutions. So it has no solutions mod 3 because it's the statement minus 1 equals 0. Doesn't even really make any sense. Okay, so make sure not to choose any primes that are dividing the leading coefficients of what you're using. So if we can look at the possible degree factors of any subfactorization that we do in a smaller field. So here is a polynomial, and I could factor it mod 2, which we're not even really supposed to pick because we need, I actually said we're not supposed to use even primes, but in any case. So if I factor this mod 2, I find 2 factors, and one of them is degree 1, and one of them is degree 4. So this means that the actual factorization is either into 1 or 4 or 5. Okay, that's the only possibility. You can't generate more factors over the integers than you have in any residue class, right? It's always going to be, this is like the most number of factors you can ever expect to get. If I take the factorization mod 3, I get a irreducible factor of degree 1 and an irreducible factor, irreducible factor of degree 1 and irreducible factor of degree 4. So this means my factorization is either into degree 1 and 4 or 5. If I try it with 5, that's a bad prime, so we just skip it. And if I do it with 7, we find that we factored into degree 2 and degree 3. Right, so if you study this, basically the only permissible factorizations are going to be the ones that are in the intersection of all of these sets. And if I intersect them, the only thing that's left is 5. Right, so this is saying the only factorization of this quintic is into a quintic, which means it's irreducible. Like, we can't factor it. So this is just a little piece of technology that I want to show you. It's not in your project, but it is possible to determine if a polynomial with integer coefficients is reducible or irreducible by looking at its factorizations over residue classes, right? By limiting the coefficients to prime fields. This is the whole punchline of all of the hours of labor that we've been putting in. Last time I checked, this is the second best factorization algorithm that we have. The best one is basically this plus a bunch of extra optimizations that are just going to serve as distractions. But this is a real beautiful piece of technology. This is a very clever algorithm. It was amazing to me when I was shown this. So let's get into it. So here's our setup. You're going to give me a polynomial, and it's going to be from ZPX, right? So it's going to be a polynomial in X with coefficients taken from ZP. It's not an integer, right? It's at least a polynomial of degree 1. It is square free. That is, the GCD of A and A prime is 1, right? So that's our setup. So that means the factorization is certainly going to be into a product of irreducible monic polynomials. The question is, how can we compute the linear factors of A? Let's focus one by one, right? So here's the first idea. So if we're in ZP, how many possible roots are there for this polynomial? Okay, let's remind ourselves what a root of a polynomial is. If f is a polynomial, if f of x is a function which is a polynomial, if f of p is 0, then that's a root. Okay, so you have a polynomial. What are the things we're allowed to evaluate if we're working ZP? 0 to p minus 1. That is to say, there are finite many possible roots of this function. Okay, so you give me f, you're telling me we're in ZP, and I'm just going to say, is it 0 at 0? Is it 0 at 1? Is it 0 at 2? Is it 0 at 3? These are just evaluations. And if I get lucky, it will spit back 0 at me, and I'll say, aha, I found one, right? F of 7 is 0, and therefore x minus 7 must divide this, and I found a factor. Okay, that's not too bad, but it's still not very clever to like do all of these tests, right? Maybe p is quite big. Is there a way that we can like get all of the linear factors simultaneously? So let's consider this polynomial. What is it? It's the product of all linear polynomials in this ring, all of them. So what happens if I take the GCD of the thing I'm trying to factor with the product of all linear polynomials? What is that GCD going to be? The product of all the linear factors of that polynomial. We found them all with one GCD. Now it's still, we have to then take that and factor it further, but we've at least know we have a quantity which is the product of all linear factors. And we'll discuss then what to do after that. Okay, so we've taken our polynomial, we've extracted the product of all linear factors. It's not factored yet, but we know that it's the product of all linear factors. How then do we then reduce that further? Well, why don't we pick half of these? I'll find a polynomial which is product of half of all the linear terms, and I'll take the GCD of that. What are the options here? Well, either the product I found is totally inside half of those things, or it's totally outside, in which case, okay, so if it's totally in, the GCD of it and the half the factors are going to be itself, not useful. If it's totally out, the GCD of that and all of the product of half of the linear factors will be a unit, 1, also not useful. However, there's another option where the product of all the linear factors is like half inside that, partially inside that. And if I take that and the GCD and I find that they're not 1 or G, then I've managed to take the product of all linear polynomials and decompose it, right, into 2 factors which have lesser degree. And then we just repeat this process until we find all the linear factors. Ask me questions if this doesn't make sense. So let's start again, right? So like this is a product of all linear factors of our in ZPX. Therefore, if I take the thing I'm trying to factor and I find it and I take the GCD with that product, what I'm going to get back is the product of all linear factors. Like, and it's not going to be factored. It may be a quintic, but I know it's the product of all linear factors. So the secondary task now is, well, then how do I take this quintic, which I know is the product of 5 linear factors, and actually find those linear factors? And I'm saying, well, take the product of like half, like literally cut this in half, like the product of all linear polynomials, and then take the answer that you have, this quintic, and take the GCD with the product of half the linear factors, and maybe we'll get lucky, right? Maybe the GCD is going to be not 1, not G, but something else, like a quadratic, in which case I have that quintic, and now I've separated it into a quadratic and a cubic, which are smaller. And then I just repeat the process until we hit the ground, until everything is units. Does that make sense? Because this is like the whole driving piece. Like this is the whole it's just going to get more complicated from here. Yeah. Well, what we're going to do is a random permutation of this. And I'll tell you how to do that. Right? We just have to sort of like permute all of the roots around a bit because it won't be good enough to have like just two. We need to like randomly permute this until we get lucky. And we're going to get lucky 4/9 of the time, which is enough. Yeah. You only have to do like 2 or 3 times to be more greater than a half. Yeah. No. Well, I can at the end, right? Like after we go all of this, but like ask me questions, right? Because this seems, yeah, this is going to be important.
What's up there was different to what I heard you say.
Okay, so where's the discrepancy?
What I heard you say was after we get like the GCD from idea one, so we maybe we get infinity.
Yeah.
Then we plug that back into the GCD and then we use.
But we give it less, right? We're taking the GCD with like half of the linear factors. Where at first we did it with all of the linear factors.
Yeah, but
Yeah.
in idea two, it says A instead of like what we got from idea one.
Oh, okay. So I suppose I shouldn't have used A. I should then say this is the thing that was spit out by idea one. Okay, fair. I'll clean up some of the language. Yes, sir. Sure. X minus 4, yeah.
So is that
just round? Yeah, it doesn't matter. Yeah. Yeah, but it's going to be simpler than that because I'm going to tell you how to just randomly permute the polynomials or randomly permute the roots. This is actually what, yeah, that's what I'm saying we should do. Like, I'm not saying like we're splitting this in half. I'm saying randomly take half of them effectively. And then if that doesn't work, randomly take half of them again and try again and keep doing that until it works. Right? Okay, so this is a process for us to at least factor all of the linear irreducible components of the thing that we're trying to factor. Okay, how do we do this then for the rest, like the quadratics, the cubics, the quartics, the quintics? And the answer is exactly the same way, which is kind of remarkable. Okay, before we get into that, who remembers Fermat's Little theorem? Anyone study this? A little. If P is a prime greater than 2, which is why I provisioned that, and A is strictly positive and less than P, then this is always true. A to the power of P minus 1 is congruent to 1 mod P. Okay, or equivalently, A to the power of P is congruent to A mod P. Or equivalently, A to the power of P minus A is congruent to 0 mod P. Let's check this, right? So A is 5, P is 23. So 5 to the power of 23 minus 5 mod P should be 0. That's what I'm saying. Hooray. Let's do it again. I'm saying A is 15, P is 29. A to the power of 29 minus 15 mod 29 is, that's wrong, right? Unless I just prove Fermat wrong, which seems unlikely. What happened here? I know it's written on the board. Overflow, right? Why was it sort of silly to do it like this? So I'm saying that we're working in a number system with exactly 29 numbers. How many digits does 15 to the power of 29 have? Let's find out. Oh, overflow. I need to do this in Python. Yeah, that's the punchline. Oh. Oh, you can't see it. Sorry about that. I have to. Right. How do I make it big? I just say big. Just for the 15. Okay. How many digits is, how do I do a log? like this, I hope. Oh, log 10 without the square brackets. Okay, it has 34 digits. Okay, but like I only need like 28 was our biggest number in this number system, right? So it was like totally pointless, right, to let the number grow to that number just to find its image mod 29. That was like exceptionally unwise to do it this way. So what you need to do instead is like make sure you're doing a mod every time you take a product, right? Because the subproduct should never exceed 28, right? So this is one of the tasks in your homework to fix this, right? And it's there's a big long explanation about this at the end of this if you want to get extra explanation. I'll talk about it if we have some time, but there's one of your tasks is about optimizing PalMod, and this is a much better explanation. Okay, so where were we? Okay, so yes, if we convert to big integers, then this is going to work, but this is one of the things that you're going to have to correct. Okay, so corollary. Like, take a look at this polynomial then, x to the power of p minus x in ZP. What's true about this polynomial? Right. So what is it? Which means it's the product of all linear factors. X to the power of p minus x in ZPX is the product of all linear factors because every number in that number system zeros it. Right? But isn't this really important to have this polynomial? Like the whole thing that I was doing before was taking A against the product of all linear factors. That's not something I want to explicitly generate. It just happens to be this. This is the product of all linear factors mod P. Right? So what we need to do then is take our GCDs against this. What kind of polynomial is this? Is it dense? No, it's about the most sparse polynomial that you can possibly have, right? So I said it's going to be important for us to utilize sparse polynomials for factoring, and it's for exactly this reason. We're taking GCDs against, these are sort of called cyclotonic polynomials. They're aggressively sparse, so we need to optimize for taking GCDs against them, right? So, okay, so we can do our GCDs. We can now generate the product of all linear factors super quickly because it's just that. So then how do we take this now and get all the quadratic factors and cubic factors and quintic factors? This is another polynomial, and amazingly, this is going to be the product of all monic irreducible polynomials of degree d that divides k. Okay, so let's look at this, right? So if k is 1, this is the product of all irreducible factors whose degree divides 1, linear factors, okay? If k is 2, this is going to be the product of all irreducibles of degree 1 and 2, okay? If k is 3, this is going to be all irreducible factors of 1, 2, and 3, I swear. And then if k is 4, it's 1, 2, and 4, right? Those are the things that divide 4. So how is this useful? Well, okay, you're going to give me a polynomial to factor. I'm going to take its GCD against this, which is the product of all linear factors, and I'm going to get all of the linear factors, and then I'm going to remove it from the thing I'm trying to factor. So all the linear factors are gone. Now I'm going to take the GCD of what's left against x to the p squared minus x, and that's going to give me the product of all quadratic irreducible factors, and then I'm going to remove that. Then I'm going to take the GCD of what's left with xp cubed minus x, and that's going to give me the product of all cubic irreducible factors. And we keep doing this, right, until we hit a degree, like you do it until the degree of the polynomial. But actually, you can be a little bit smarter, right? Because if you found previous factors, you don't have to go, like if you're trying to factor a syntic and you found a cubic 3 linear factors, you don't have to go all the way to 5, right? You know what's left is a quadratic factor. So you could do some optimizations here. Okay, so here's the pseudocode for this. So what this is going to do is, so we have to do these factorizations in two parts, right? You give me the function, you give me the polynomial. I'm going to return to you a list where the list is a product of all the linears, a product of all the quadratics, product of all the cubics, quartics, syntix, and then so on. Yes, sir. Yeah, not equal to. Oh, sorry, this is pseudocode. Do you want me to change it? Which one do you prefer? Sure. Doesn't matter to me. As long as it's unambiguous and you guys can interpret it. That's pseudocode to me. We picked this because it's not possible to satisfy that condition. It can't be less than and greater than at the same time. Okay. So that's how this is going to work, right? And then, in fact, we've actually already implemented for you this in Julia. So let's go a little bit further. Okay, so consider that we know how to factor the differences of, remember that we know how to factor differences of squares. So now we have to, now that we have groups of factors, we now need to focus on like, well, here's the product of all irreducible quadratics. I now need to like decompose that into quadratics. And this is how we're going to do it. This is the second idea. So consider that we know what differences of squares factor to. A squared minus b squared factors to a minus b, a plus b. That's just known. Okay. So look at this polynomial, which is the product of all linear factors. So first notice that I can factor out an x. What is this? Remember, p is not 2. So p is certainly odd, which means what about p minus 1? It's even, which means this is a difference of squares, right? So it has a predictable factorization. Okay, so what is this? Well, if this is all the product of all linear factors, this is going to be half of them. Has to be, but I'm saying, well, half plus minus 1. Yeah? Okay. Because that has to make sense, that this is super important, right? That taking the difference of squares is the thing that's actually allowing us to separate these products. Right, so this must be a product of half the roots. Thereby, right, so if you give me, so you're now giving me maybe a cubic, and I'm saying, oh, this cubic is certainly the product of 3 irreducible linear factors. I'm going to say, okay, cool. So now I'm going to try to take the GCD of u in half of the linear factors and hope that I get lucky, right? Because if I generate a proper divisor of g, then I have reduced the problem into 2 smaller factoring problems, and I just repeat this. Here's something critical. Here, this was sort of x minus 0. I didn't really write it, but that's what it is. If you want to randomly permute all of the polynomials, you just put x plus alpha there for any alpha that you want, like preferably not 0, otherwise you're generating this. So doing x plus, I can say x plus alpha to the p minus 1/2 is a product of all the linear irreducible polynomials with all of the, like we've permuted around all of the roots, right? So you just have to change this alpha to generate a new random permutation along the GCD. So similarly, if I increase the power of p to the k, like it's also a difference of squares, and it also has this predictable factorization, and thereby this is going to be a product of half the monic polynomials of degree k, but more appropriately for all k that divide pk minus 1 over 2. Jeez. Okay, I'll just do this last one and then we'll figure out how to fill in the rest. Okay, so suppose gk is a polynomial that has coefficients taken from zp, and it's the product of monic polynomials of degree k. Like that is to say, like, oh, here you go. Here's the product of all irreducible quadratics, but that's as far as I can take you. The probability that taking the GCD of that and half of the quadratic irreducible factors after this random permutation is greater than or equal to 4/9. And this is important, right? Because this is a Monte Carlo algorithm. This is a random probabilistic algorithm. So we want it to work reliably, right? So it works about half the time, which means on average, you're only going to have to do maybe, I don't know, 2-3 guesses, and like it should work. If this was really small, if this was like 1 in a million, then this is bad, right? Then we might as well be searching for the roots linearly. Okay, so all that remains is to utilize the previous two algorithms, right? So the factoring algorithm works like this, right? So you give me something that's square free. I take that and I say, here's the product of all of the monics. Here's the product of all of the irreducible linears, irreducible quadratics, irreducible cubics, irreducible quartics. That's phase one. Phase two is taking that and then utilizing this stochastic algorithm to take that and actually factor it. So take the cubic and factor it into a product of 3 linear irreducibles. So then we generate like another list where we have all of the irreducible components, but none of the degrees, right? We've lost all of the degrees. So the final step is to take that list and just do trial divisions. I'm saying here is a irreducible factor. And I'm going to say, okay, here's the thing I started with. How many times do you divide that? Okay, that's your degree. And you have to do it for all of them to recover these degrees. And then, yes.
When we check that G divides that,
Yeah.
we just check that the remainder is zero.
You don't have, it's guaranteed to divide it.
Yeah. But
Yeah.
Like, let's say I want to check how many times it goes into F, for example.
Yeah.
Then at some point it's not going to divide.
Oh yeah, I suppose you do trial divisions until you don't generate a clean division. Yeah, you're correct.
Would the check be just see if the remainder is zero? Is that how we would check if it divides?
Yes. Yes. Right. You just have F, and I'm saying divide by X minus A and keep doing it until somehow I can't. Right. Okay. And then finally, so the original problem, remember we made that polynomial monic. So it's like, okay, but like, how do we add that leading coefficient back in? So I just say, what was your original leading coefficient? And you can say like, I don't know, 6. I'm like, okay, I'll just multiply by 6 now. Because what I have is monic. What I have is like all unit coefficients. So if you just tell me what you want your leading coefficient to be, I'll just like stick it in as one of the factors. Right, so I can factor like 2x minus 2 into 2 and x minus 1. Right, so we can always just stick the leading coefficient back in at the very end with no energy. Because if I knew the original polynomial had leading coefficient 3, okay, then I just put a 3 back in because what we have is monic. The rest is just sort of expanding on some of your tasks. Like, so for example, this is a much lengthier explanation of the power mod algorithm that you have to implement. And then down here are some implementation hints that were relevant last year for heaps, but like it's basically, if you just pull out heap and put in this linked list, it's sort of morally the same. Now, that's it for tonight. So we're gonna have a consultation on Wednesday, and we're gonna meet again on Monday. And on Monday, it's your time to like ask me more questions, right? So I need you now to go study this material. And then on Monday, you come back and you say, I don't understand the following things, or we found these mistakes. Because I know this has gone kind of fast, but Yanni gave me a directive to get all of the information to you so you can do the project. So study this. We'll come back on Monday and we'll like discuss it again. And then we can clarify anything that's still lingering. Because I know this may have been fast, but I had to get through it. I can also expand in it, but read through it. I put a lot of energy into actually like writing around the things that I was talking about. Okay, so I don't want to keep you hostage. So you can go. Yeah, thanks, Max.